a lot of natural phenomena leads itself to being described in terms of exponential functions, where in particular we describe something that follows growth or decay in terms of exponents using things of form f of t, or a is equal to a0 e to the kt, where, to be a little bit more particular about how these things work, we have that when k is equal to 0, this is a growing entity, this is a growth model, where a0 is the initial amount, a is the amount it has at some time t, and k is a constant value representing the growth rate that the model follows. Meanwhile, if k is negative, then this follows a decreasing pattern. This is what's called a decaying entity, where a0 is again the initial amount, t is some amount of time t, a is the amount that you end up with after that time t, and k is a constant that represents the shrinking or decaying rate. And often the types of problems we have, the types of problems we're going to see here in particular, are ones in which we want to find out what's going to happen in terms of that constant value k defining our growth or decay rate. Because we usually will have some amounts we're going to be looking at, we have some amount of time we're considering, and we know what e does. So really that all leaves us to have to figure out k. And then from there we can do other things with the model in terms of other amounts of times. So let's get some examples here to see how this sort of thing works. For our first example, we have that in 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million, that is 1.052 billion. Use the exponential growth model A equals A0 e to the kt, where t is the number of years after 2000, to find the exponential growth function that defines the model. And then predict, using the model, at what year the population will reach 1.5 billion. So for this, we're going to use that type of model we have there, where we are given that A0 is equal to 807 in terms of millions, and that A11, it's not really the best notation how we write this, but I think you get the point, is 1052. So we have 1052 is equal to 807 e to the 11k. And then from there, we just want to solve for k. So this is going to be the sort of basic exponential equation model. We're going to pull things around, take some things to the natural logarithm to get rid of those e's. What's going to end up happening here is we have e to the 11k is equal to 1052 over 807. Then we're going to apply a natural logarithm to both sides. We've done this a bunch of times, so I'm not going to write that whole step out here, but if you apply a natural log to this, what you'd be left with is 11k, and on the other side, you'd have the natural logarithm of 1052 over 807. Just throwing in that natural logarithm to help ourselves out. So we would end up getting there that k, in this case, is equal to the natural log of 1052 over 807 divided by 11, which is a really nasty number. So even though under many circumstances I'd prefer this kind of answer for its precision, in the context of this application it makes more sense to round off and say that k is about 0.024. Again, this would be technically better, but it wouldn't really be worth the effort of chasing around an exponent quite that nasty every time you want to make a prediction. Like in that second part there, where if we want to find out how long it takes to get 1500, that is 1.5 billion, what we would have to do is solve the exponential equation 1500 is equal to 807 e to the 0.0024 k. Excuse me, not k. Silly. T. Sorry, we know k now, we need to find t, but I made that mistake because it's literally the same process. It's just here, instead of knowing 11, we know 2/100ths. But we're going to do the same thing. We're going to divide over those terms. We're going to end up with something like e to the 0.0024 t is equal to 1500 over 807, which means we take the natural logarithm, we're going to get 0.0024t equals natural log of that thing. So if we want to get t, I'm going to try and give lots of space here because I'm going to want to make this look a little bit bigger. We'll have the natural logarithm of 1500 over 807 divided by 0.0024, which, I misspoke when I was talking about this one, but it's the same sort of idea. We didn't want to carry around a whole bunch of things there. In this case, we want to get an actual number of years, t, so we have that this would take about 26 years, which in our language, in the language of our model, means that you would expect the population of Africa, based on this projection, to hit 1.5 billion in about the year 2026, where there might be some room for variation depending on exactly when you measure that, and other factors that could have affected the model that wouldn't have been predictable in the year 2000. Where the next thing we're going to look at here is a different sort of exponential model in terms of a very special thing for elements called half-life. We're going to be talking about the amount of time it takes for an element or some piece of matter to decay to half its value in terms of this kind of model.